Hello everyone. I wanted to talk about a few things here that we touched on briefly in class. We'll be looking at the relationship between delta G, cell potential, and K, the equilibrium constant. And we'll be doing some examples here. One thing I want to mention, you'll notice that I'm pretty loose with the definition or with the language I'm using here for delta G and cell potential. I'm not specifying standard state. We will have some examples where we are going to be using standard state and some where we will not be. So the first one, you'll notice that the example says delta G at standard state from half cell potential. So there we will be using standard state. However, when we use the Nernst equation in the next example, we will not be. And then finally, we'll talk about how batteries work. This is not something that we had looked at in class previously, so this will be kind of a new idea, and we'll pick up from there when we go back to the live lectures the next time we have class. So just a reminder, this is that relationship. This is something you do want to understand, how thermodynamics and electrochemistry are basically two ways of looking at the same thing. And then equilibrium is a third way. So we have three ways of describing these things. So we could be doing it in terms of delta G, we could be doing it in terms of cell potential, or we could be doing it in terms of equilibrium. You want to know this both qualitatively and quantitatively. So when I say qualitatively, what I mean by that is that you look at the aspect of the number to decide something. For example, whether or not it's spontaneous. So delta G at standard state less than 0. So if that's negative, that would say that's a spontaneous reaction. Whereas for the cell potential, if that is positive, we have a spontaneous reaction. And then for equilibrium, equilibrium greater than 1 means spontaneous. So we could have the sign or the size of the number to determine that. You also want to be able to use the equation shown here to relate between different measures, so be comfortable with all of those equations. And Faraday's constant we introduced in class as well. Okay, so I want to go ahead and look at an example. We are going to do the first example here in this recording, and if you would like additional practice, I will leave the second one to you for that. So the first one is looking at finding delta G. The second one is looking at finding K. So they're somewhat different questions, but we're essentially using that idea of equating the three. So they will be similar in that way. So I'm going to go to my recording, and we will, or my camera, and we'll go through this together. Okay, it says use the tabulated half cell potentials to calculate delta G at standard state for the following redox reaction. So we're showing the reaction here. I'm going to go ahead and write the half reactions. So aluminum reacting to form aluminum plus 3 is one of the half reactions. And then the other one is magnesium plus 2 reacting to form magnesium. Okay, so what we want to do first is we want to, and then let me, I almost forgot here, we also have the electrons, right? So 3 electrons are lost there, and then we need 2 electrons for this one to work. And then we can see how going from here to here, we would have had to balance that. We're not balancing that right now. That's not what we're focusing on. But then we want to find these on the standard reduction table. So I have a copy of that over here. Remember, these are all going to be reductions, so they one of them will have to be kind of turned around. And so looking over here, I see down here magnesium. I'm going to go ahead and circle that. So magnesium plus 2 electrons going to form magnesium ions plus 2 electrons forming magnesium. The voltage for that was negative 2.37. And then the other half of the reaction is aluminum. And actually that is directly above it. They're right next to each other. So those two are neighbors. So there we have aluminum plus 3 electrons going to form aluminum ions plus 3 electrons forming aluminum. And we have the potential there is 1.66. Negative 1.66. Okay? So these are both negative. And what we want to do, so these are the, I should be careful how I'm stating this. These are the ones from the table. So I'm going to write reduction potentials there. These are both reduction potentials. This one is the same as what we're doing. This one is different. Okay? So just be aware of that. This one is the same. This one is different because this one is reversed. So in writing down the reduction potentials, so what we'll have for this reaction is we'll have this one will be flipped around. Okay, so what we'll have is, I'm going to write it like this. So the potential for magnesium minus the potential for aluminum is the cell potential. So we'll do the math there. So we have, for the magnesium, we have negative 2. Oops, let me start over there. Okay, so we'll do the math here. We have 2.37 with a negative sign. And then we're subtracting a negative. So I'm going to put that as a positive. So plus 1.66. And that's our cell potential. So we have negative 0.71. Okay, so that is our cell potential. So that's negative. So that's maybe telling us something about what's going on here in terms of whether or not it's spontaneous. Okay, so we found the cell potential. F is Faraday's constant. Now we need to know N. If we look up here, we have different values of N from one half reaction to the other. This N is for the entire reaction. So if we look at the entire reaction, so we had to multiply this one by 2, this one by 3, we have N is equal to 6 electrons. So if you look at this, hopefully you can look at this to see how that would work. So 3 magnesiums plus 2 forming 3 magnesium, so 3 times plus 2. So we need 6 electrons there. And then here we have 2 aluminum going to 2 aluminum plus 3. So the plus 3 we would need to be gaining, or we would be losing 6 electrons there. So the N is 6. It's for the entire reaction. So delta G here would be 6 electrons times Faraday's constant, 96,485. And the units there are coulombs per mole of electron. And then the cell potential we found was 0.71 units there are volts. Okay, so we'll do the math. So negative 0.71, and then let me put the parenthesis there, times 6 electrons times 96,485, and we get this. The units here would be joules, so I'm going to divide by 1,000 so we get kilojoules. We'll often want to do that. Remember there's a negative sign here. I should put that in here as well, right? So that equals a negative, and then we have a negative over here. So this will be positive. So positive 411 kilojoules would be what we get there. And just to think about that, what does that mean? That means that this is non-spontaneous, and we could have come to that conclusion by looking at the number up here as well. So positive delta G is non-spontaneous, negative voltage is non-spontaneous. And we can see that answer is the same as what they're listing there for A. So let's go ahead and return to the PowerPoint. And so you can see that is the correct answer. I will let you do this one. It will be somewhat similar on your own time, but the answer will be listed there. We went through talking about concentration cells, and you got an example of doing this in the lab. So what we're going to do is we're going to move on and talk about the Nernst equation when we have something other than a concentration cell. We can use this in cases where we're not looking specifically at a concentration cell. So same idea, we're using these relationships, however not at standard state, so we account for that with that additional term. Okay, so the question says, calculate the cell potential for the following reaction that takes place in an electrochemical cell at 25 degrees Celsius. So we're given the cell notation here. So first thing I want to do is maybe write this as a chemical reaction. So we have the anode and we have the cathode. So we know what happens at the cathode is we have the ions reacting. So the ions are reacting at the cathode. The electrode is reacting at the anode. Okay, so ions reacting at the cathode, electrode reacting at the anode. If it is an inactive electrode, right? So there are examples of where you would have an inert electrode, but that's not the case here. And then we also have the cathode as the product, and we have the at the anode we have the electrolyte reacting. So this is our balanced equation. One other thing I should mention, and I kind of skipped through how I got to this, we have tin is a +2, silver is a +1, so we need 2 of those for that to balance. So if you need to go through and just double check that, that's how that is happening. So the 2 half reactions here, we have 2 electrons reacting with tin to form solid tin. Again, I'm writing here the reduction half reactions. So these will both be as reductions even if they are not a reduction in the reaction itself. So here we're showing the silver again as a reduction. So these are the 2 half reactions. And then what we'll do is we'll look on our table for these reactions. Again, this might be difficult to see, but you have your own table. The silver will be up here. We can see for silver we have that is the reduction potential. So we'll go ahead and write that in. So 0.80. And then for the 10, we find 10 is, okay, there's this 10. This is not the 10 we want. That's 10 plus 4 going to 10 plus 2. Here we have the 10 we want. 10 plus 2 going to 10 solid. And so we have that value. Okay, so we have negative 0.14. So for the for the cell potential, what we'll have is the cathode minus the anode. And so what we have for the cathode is what's going on over here at the silver, so the 0.80, and then minus the anode. For the anode we have the 10, so minus 0.14. Okay, again, we're always flipping one of them around. We only flip it around once, right? So we don't flip it around up here and then flip it around again down here. So we only flip it one time, and you get 0.94 when you add those together. Okay, so that is if it was at standard state. It is not at standard state, right? It is at some other conditions. We're showing here different concentrations, so we need to take that into account as well. So we will need to use the Nernst equation. So the Nernst equation, the voltage of the cell is equal to the voltage of the cell at standard state minus 0.592 divided by N times the log of Q. And we need to figure out what all these things are. So we've already found this one, right? So this will be the 0.94. That's voltage. And then N from up here we see is 2. So 0.592 divided by 2 for the log of Q. So for Q we're going to have, let me actually do Q over here, and then we'll put that in. So we have products over reactants. Products over reactants. So if we look up here at our balanced equation, we leave out the solids. So the products are the 10 ions. The reactants are the silver ions. Products, reactants, leaving out the solids. Okay, so Q here is going to be the 10 concentration divided by the silver concentration. Okay, now there's one other thing we need to take into account here. For the silver we have 2 of them, so we need to square that. So silver concentration squared. Okay, so this, again, we did Q in the last chapter, so same thing here. So for the 10 concentration we had 1.8. For the silver concentration we had 0.055, and that is squared. Okay, so let's go ahead and bring out our calculator. So we have 1.8 divided by 0.055 squared. Okay, and that's what we get. Let's see, actually that's not the final answer. Okay, so then equals 595. Okay, so that's the value of Q. One thing you can do on that, so we're doing a lot of calculations there, so a number divided by a very small number squared, you would expect that number to be bigger, so you would expect this number to be bigger than the 1.8. So that's how I knew when I looked at my calculator that something wasn't quite right. So we'll put the log of 595. That's what we found for Q. Q doesn't have units, so when we do the log, we're not taking any units into account there. So I'm going to do the log. So this is the base 10 log with the Nernst equation. And I'm looking for that on, here it is on my calculator. Okay, so we get 2.77. I'm going to write that down here. Just in case something goes wrong, it's good to write down the math steps when we have this part of the equation where we have a bunch of stuff log something, and then we multiply that by that constant 0.592. and then we divide by 2, and then we get for all of this part 0.082, and then we had the 0.94 going with that. So I'm going to go 0.94 minus 0.082, and we get for our final answer I'm going to call that 0.86. Okay, so that's the voltage, and we can see that that's one of the choices there. So I'm going to go back to the PowerPoint. So we did this first one. You can see the answer there. That's what we got. And I'll let you do the second one on your own if you want a bit more practice. We did a calculation of a concentration cell in class already, so we won't go through that again. But if you have questions on that, we can definitely spend some time on that when we get back together. Okay, so I want to talk a little bit now about how batteries work. These are basically based on the same thing we have just talked about with voltaic cells, where you have two half reactions going on, and we have electrons going from one to the other. So inside of a battery, you have a cylinder going down the middle. In this kind of a battery, this is the cathode, so we'll talk about what goes on there. It's, in this case, an inert electrode. And then you have the cylinder, which is the outside of the battery. And sometimes this is called an annulus, so it's a kind of like a ring with an empty part in the middle. And that empty part is the salt bridge. So there's a paste in here that is essentially acting as the salt bridge. At the anode, which is the outside, we have this reaction. So essentially, the shell of the battery is what's corroding as this takes place. So zinc going to zinc plus 2. So the zinc metal on the kind of outside of the battery will go into dissolve into the salt bridge paste. There is an additional layer outside of what we're calling the anode here, so that it's not like the whole thing's going to crumble when it's all done. And then we have close to the graphite rod, we have this other reaction occurring where we're changing the oxidation of the manganese. So it is a solid as that's taking place, and it's surrounding basically the cathode. A couple of things about this setup. So it doesn't look like two jars that we have, a wire between. That's just an inconvenient way to do things. So if you can imagine, every time you wanted to plug something in, you had to walk around with two jars of liquid, right? So this is a better engineering design to kind of fit everything into the same space. But it's doing the same thing as what we've seen in all these voltaic cells. This is another type of battery that you have in your car. One thing, if you look at the reduction potential tables, if you look at the very top to the very bottom, we have at the very top you have fluorine reacting with a voltage of almost 3. At the very bottom you have lithium reacting with a negative 3. So if you put those together, so the best possible reaction you could get would give you a voltage of 6, right? And that is a very destructive reaction. It's not actually a reaction we would want to have happen. But we know that in our cars we have 12-volt batteries. So how does that happen? How do we get 12 volts from a battery if we know that, the biggest we can get, the biggest difference is 6. So we'll talk about that as we look at the lead storage battery. So how this works is you don't have one battery, you actually have 6 batteries. So the battery in your car is made of 6 batteries. And so we put those batteries are in series, so you go from one to the next, to the next, to the next, all the way through all 6 of them. And essentially what that does is it gives you a bigger potential difference. So imagine having 6 tiny waterfalls. The difference in elevation is similar to the difference we're seeing in the potential here. So each one of those cells has a voltage of about 2 overall. So 6 cells with 2 each gives you the 12-volt battery. These are rechargeable. That's kind of important that they are rechargeable, and what that means is that the reactions will go in reverse. And why is that important that it's rechargeable? Well, when we run our car, we're recharging the battery, so the alternator in your car is putting that energy back into the battery, and and then the battery is using that energy to run the lights and the radio and all the other things. If you didn't do that, your car battery would run out very quickly. So a couple of things there. First is the recharging, and then secondly is the fact that it is in a series. Lithium-ion batteries are another type of battery that's become important in the past, the past decade or so, maybe more than that. So what's happening here is that we have lithium ions moving through as well as electrons. As the lithium ions move, the electrons are moving in conjunction with that. These are also rechargeable, so we often have these in our cell phones. They're light, so that's convenient, and they tend to last a bit longer. So lithium-ion batteries is another type. Finally, we have fuel cells is a type of battery where the there's actually a chemical reaction going on, and it's going on in different locations, and from that we get a charge. With a fuel cell, you have to have a supply of the fuel to continue to have it occur. So here we're showing a hydrogen-oxygen fuel cell. If you have hydrogen coming in one place, oxygen coming in the other place, they will react to form water, and this can be done in a way where we can get electricity to come out of that. So this is an area of research. The difference between a fuel cell and a battery is you're continually supplying reactants to a fuel cell so that it doesn't basically run out of charge. So those are some different types of batteries. We will look at additional applications at the end of the chapter, and I will see you all when we are back together on Zoom.